Alright, let's try out a couple examples using our arc length and area of a sector formulas. So first thing we got here is a circle. Central angle is indicated as 140 degrees with a radius of 9 inches. So first and foremost, I'd like to remind us of what the arc length formula is. This is going to be S is equal to R times theta, or theta times R. However, it is necessary that theta is measured in radians. You'll notice for this problem, I've given you theta measured in degrees. It's not because I'm a horrible human being. I'm a horrible human being for lots of other reasons. No, we just want to do a little extra conversion on this one. So we currently have theta measured in degrees, which is 140 degrees. What we're going to do is convert that into radians. And the way that we convert is whatever we're converting to goes on top. Whatever we're converting from goes on the bottom. So that'll be 140 degrees times pi over 180 degrees. Once we combine this into one single fraction, we'll have 140 pi over 180. If we reduce this fraction as much as possible, we should be able to pull a 20 from each of those to cancel out, to leave us with an angle of 7 pi over 9. So using that angle of 7 pi over 9 measured in radians, we can now calculate the arc length of this. So this will be S is equal to our theta that we just calculated in radians, 7 pi over 9, multiplied by the radius, which is 9 inches. Numbers work out pretty nicely here. The 9s will cancel each other out. We will be left with 7 pi inches. Now that would be our exact value. If we were interested in calculating a decimal approximation, of course, we could break out the old graphing calculator and ask it to perform 7 times pi. 7 times pi is about 22, we'll call it 21.99, because why not, inches. Now for the corresponding area of a sector, we have a formula for this as well. Area is equal to 1/2 times theta times r squared, where once again theta is going to be measured in terms of radians. Now we've already calculated theta in terms of radians, so it won't be necessary for us to go down that route. Now as far as units on this final answer are concerned, we are squaring a number of inches. And to write out a little more succinctly exactly what I'm doing here, I'm multiplying by 9 squared, so I'm going to multiply by 9 and then multiply by 9 again. Allows me to cancel out one of the factors of 9. 9 times 7 pi for the numerator is 63 pi. Denominator is 2. And again, this will be square inches, or inches squared if you prefer. Turning to the calculator, we're looking for 63 pi over 2. So if we wanted to approximate this as a decimal, this would be about 98.96 square inches. So this is one use of the formula. Another possible use of the formula would be if I do not provide for you what the central angle is. Rather, if I were to provide for you simply a length of one of the arcs and the radius of the circle, which is enough information to figure out some good stuff. So let's go out this way and this way and say that this is going to be 3 inches and that this out here is going to be a total of 5 inches. So this time I'm interested in finding the central angle and the area of the associated sector. So things that I know are R equals 3 inches and S is equal to 5 inches. What we're going to do is use the same formula as what we used above for the arc length formula. S is equal to theta times R. Except this time we know S and R. So S is equal to theta times R. I'm going to plug in the fact that S is 5 inches, theta is unknown, and R is 3 inches. Algebra necessary to solve this for theta. We're going to go ahead and divide both sides by 3. We'll get that theta is equal to 5/3. Now it's automatically in radians if you're starting with inches and inches over here. As soon as you divide inches by inches, you get a dimensionless quantity, which would be radians. So now, with this theta value, I can head back to the area formula, which was area is equal to 1/2 times theta times r squared, and plug in all of the information that I now have. r we set is equal to 3. The angle theta is now equal to 5/3. Now doing similar algebra as what we did on the previous problem, this would be 1/2 times 5/3 times 3 times 3. We could get one of those factors of 3 to cancel out. No pi's in this one. This one is simply going to be 15/2 square inches. No need to approximate on this one, as this one is exact. So, a couple examples for arc length and area of a sector.